In this video, we'll see how to use integral tables, technology, and numerical approximations for which we are not yet able to use the fundamental theorem of calculus. Most calculus books have an integral table. This includes various indefinite integrals. Some of these we already know. For example, we know the antiderivative of e to the x is e to the x plus some arbitrary constant. Here, the arbitrary constants are left out to save space. This indefinite integral is one we do not yet know. If in some application problem we end up having to compute a definite integral from, say, 0 to 2 of x times e to the x dx, we can look in our integral table and see that the quantity x minus 1 times e to the x is an antiderivative. If we don't believe this, we could check by differentiating. Here we use the product rule. And we verify that this formula is indeed correct. And now we can apply this to our definite integral. Later in the course, we'll learn a technique to develop the antiderivative of x times e to the x directly without consulting the table. But some indefinite integrals are more challenging. For example, it's possible to show, although very difficult to do so, that there is no antiderivative of e to the negative x squared that we can represent in terms of elementary functions, various combinations of cosines, sines, exponentials, logarithms, and so forth. So what happens if in an application we need to evaluate the integral from 0 to 1 of this function e to the negative x squared dx? Various technological tools such as Desmos can help us. If we type in integral from 0 to 1 of e to the negative x squared dx, Desmos will give us a numerical approximation for this integral. Wolfram Alpha will do the same thing. Wolfram Alpha displays the exact value in terms of this ERF, or error function, that we have not yet encountered. In fact, if we ask Wolfram Alpha for the indefinite integral, it will give us an answer in terms of this function which we don't consider an elementary function. So how does Wolfram Alpha or Desmos come up with this numerical approximation? It might be through a left or right or midpoint Riemann sum, or through a more advanced numerical technique. We'll consider two more numerical techniques now. If instead of constructing rectangles for this function, which happens to be 1 over x, we construct trapezoids, we can see that, well, for one thing, the trapezoids will give us an area that's a little bit too big for the integral of 1 over x from 1 through 7. This may be because 1 over x is a concave up function. You might also notice that while on the first two intervals we can see a significant error in our trapezoidal approximation, as we move along here, the 1 over x curve becomes closer and closer to a linear function. The trapezoidal approximation should get better and better. So if we can compute this trapezoidal area, we have a very good estimate of the actual area we want to find. Let's compute this trapezoidal area for the function 1 over x from 1 to 7. Here's the first trapezoid. The area will be the base, which is 2 minus 1, that's our delta x, times the average of the two heights, which would be our function value at 1 plus our function value of 2 over 2. So that's 1 over 1 plus 1 over 2 over 2. This delta x in our case happens to be 1. We have 3 halves divided by 2 would be 3/4. Our next trapezoid will be similar. Going from 2 to 3, we'll have 3 minus 2, our delta x here is also 1, times 1 over 2 plus 1 over 3 divided by 2. Our next trapezoid, 4 minus 3, 1/3 plus 1/4, all over 2. We see a pattern here. If we want to find this trapezoidal sum, let's call it T6 because there will be 6 trapezoids. Well, in each case I'll have a delta x, which happens to be 1 for our integral here, times, well, in each case I also have a 2 in the denominator, so let me factor that out. And then I have my function evaluated at 1, plus my function evaluated at 2, plus my function evaluated at 2 again, so I have twice that, plus my function evaluated at 3 plus that again. Same thing for 4. Same thing for 5. Same thing for 6. And at 7, on my last trapezoid, I only get that last value once. In our case, our delta x is 1. We'll have 1 over 1 plus twice 1 over 2 plus twice 1 over 3 plus twice 1 over 4 plus twice 1 over 5 plus twice 1 over 6 plus 1 over 7. And this becomes 283 over 140, or approximately 2.0214. Now, we can work out the exact value of the integral from 1 to 7 of 1 over dx, because we know an antiderivative of 1 over x is ln of x. Technically, it's ln of absolute value x, but we know the inputs here are always positive. Evaluated from 1 to 7. This will be ln of 7 minus ln of 1, which is 0. And the natural log of 7 is approximately 1.9459, which is reasonably close to 2.0214. You might try a left, right, or midpoint approximation for this integral to see if our trapezoidal sum is better with 6 trapezoids instead of 6 rectangles. In general, we have our trapezoidal approximation rule. This works for any integrable function, and we don't even need to know a formula for that function. All we need to know are the values of this function at our partition points. Unlike our previous Riemann sums, here we must have intervals of equal width. You'll notice this pattern here that we have our h, or delta x, over 2, and then 1, 2, 2, 2, etc., 2, 1 times our function values. We can get better and better trapezoidal approximations by making n larger and larger. Typically for large n, we would use technology to compute these trapezoidal sums. One reason we like the trapezoidal sums is they seem to fit most functions nicer than our left, right, or midpoint rectangles, and it's still quite easy to compute the area of each trapezoid. Instead of fitting a line segment between the endpoints in each interval of our partition, what if we fit a parabola through these 3 points? We need 2 points for a line, 3 points for a parabola. And then we found the area underneath this piece of the parabola from 1 to 3, which we can do because we know an antiderivative for any quadratic polynomial. It's not difficult to find that parabola that passes through the 3 points we want. We can write our parabolic function p of x as f of 1 times x minus 2 times x minus 3 divided by 1 minus 2 times 1 minus 3. So when we plug 1 into our function here, we get things that cancel, and we just get f of 1. We add to this f of 2 times x minus 1 times x minus 3 over 2 minus 1 times 2 minus 3. So now when we plug in 2, here we get 0, and here things cancel and we get f of 2, and then we add on f of 3 times x minus 1 times x minus 2, all divided by 2 minus 1, 3 minus 1 times 3 minus 2. So this function will pass through 1 comma f of 1, 2 comma f of 2, 3 comma f of 3. This polynomial is called a Lagrange interpolation. We then construct a polynomial that fits through the next 3 points, 3, 4, and 5, and the 3 after that, 5, 6, and 7, and we find the area under each parabolic piece, which we can do with the fundamental theorem of calculus regardless of what the function f of x is. We'll skip the details, but after some algebra, we arrive at our parabolic approximation rule, often called Simpson's rule, that gives us something similar to our trapezoidal rule. Instead of our delta x over 2, we have a delta x over 3 here. And instead of our 1, 2, 2, 2, 2, 1 pattern, we have a 1, 4, 2, 4, 2, 4, 1 pattern. But otherwise, this works very much the same way. For the integral from 1 to 7 of 1 over x dx, our parabolic or Simpson's rule approximation will be 1 over 3, our delta x, the width of each little interval of the partition is 1 in our case. Then we have 1 over 1, the function value at 1, plus 4 times 1 over 2, the function value of 2, plus 2 times 1 over 3, plus 4 times 1 over 4, plus 2 times 1 over 5, plus 4 times 1 over 6, plus 1 over 7. This gives us 617 over 315, or approximately 1.95873. And we can see that's very much closer to the exact value of our integral, which is about 1.9459. As we increase n, the number of intervals in our partition, we should get an even better answer. One requirement of Simpson's rule is that we have an even number of intervals in our partition.